Avantik.
Hi, I'd like to introduce myself. I'm Professor Valerie Edwards-Jones. I'm an Emeritus Professor of Medical Microbiology from Manchester Metropolitan University. I'm also an independent microbiology consultant, and I was asked through NOLEX if I could help to evaluate a robotic UV system, and I did this with the laboratory Melbeck Microbiology in the Northwest. So this is a presentation about the evaluation and the organisms that we used and the results we obtained. So one of the biggest problems we face in the UK going forward and globally is the threat of antimicrobial resistance. It has become bigger and more of a threat over the last 20 years as we've started to realise many of the common pathogens we see on a day-to-day basis are resistant to the common antibiotics that we use to treat infection with. If this persists and continues, it will be the end of modern medicine as we know it. You won't dare go into hospital and have something like cancer treatment or a bone marrow transplant when you're at risk of acquiring a healthcare associated infection which can't be treated with antibiotics. So it is a huge global risk, a huge global threat that's going forward, bigger than cancer, bigger than diabetes. So we are faced with the challenges of trying to eradicate superbugs. Sometimes the term superbugs can actually be misleading. And most people think when you talk about superbugs that they are very, very difficult to get rid of. Well, they are if the patient has sepsis or they have an infection associated with one of these superbugs. However, they are just bacteria as we've known and loved them. What they have is they have genes within their DNA that encode for resistance to the common antibiotics. So they are antimicrobial resistant. They are still susceptible to many disinfectants. They are still susceptible to many alternative treatments. And as such, they are susceptible to ultraviolet light. How does ultraviolet light work? Well, it works by interfering with DNA. So it passes through the cells very quickly with photons, and it intercalates with the DNA within the cell. And you have to remember, bacteria do not have a nuclear membrane, so it interferes directly with DNA, and it causes what you call dimers. So the DNA is made up of lots and lots of amino acids on a particular chain. It's all twisted, etc., if you remember DNA biology. But what it forms the amino acids to actually link together, so it disrupts the DNA. And unfortunately, after the UV has had a go at this DNA, it's very, very difficult to repair. It also intercalates and disrupts DNA very, very, very quickly, within minutes. Not within hours, but within minutes. So it makes UV a very good alternative for disinfection of the environment or a room. We've actually used ultraviolet light in laboratories for many, many years. We use it in cabinets to disinfect the air. We always have a particular glass shield in front when we're using it. We have our arms in cabinets, but we use it when we're undertaking aseptic techniques. So microbiologists have known for a long time that UV is excellent. However, it's more difficult to get integrated into the hospital environment as a routine decontamination device because there are problems with things like shadowing, etc., in the environment. And if you just think about it, if you have anything that is placed in front of the UV device, it will form a shadow. So the amount of UV that will be hitting something within the shadow, and if it's a bacterium, it means it's not receiving the amount of UV it needs to disrupt the DNA. So people have been very concerned about shadowing and shadowing effects with many of the UV devices. And it is a problem, and I've done many studies now, and I've shown that when you are in very deep shadow, the reduction in organism numbers, that's usually very rapid, is decreased quite markedly. So we were approached by UV Disinfection Robots company to actually undertake a study in the UK. They had done previous studies in Denmark and showed us the data from that, which looked extremely encouraging. So previous studies were undertaken in Denmark using the 4 common organisms that are used for disinfection testing. These are Staph aureus, Enterococcus hirei, Pseudomonas aeruginosa and E. coli. Now there are subtle differences between the Staphs and the Enterococcus and the Pseudomonas and the E. coli. So the Staph and Enterococcus are gram-positive organisms, frequently found in dust. Pseudomonas aeruginosa and E. coli are usually found in wetter areas, so such as bathrooms, etc. Staph aureus and Enterococcus are far more hardy in the environment. They survive longer in the environment, whereas Pseudomonas and E. coli don't survive very long in a dry environment. So these organisms were tested, and they were exposed to the UVD robot in a hospital setting. And what was found was that there was a greater than 5 log reduction in organism numbers within a 5-minute period, a 5-minute exposure time, when these organisms were actually placed on coupons and in proximity of the robot. Usually they're tested at a 1 metre proximity. And greater than 5 log in 5 minutes is absolutely exceptional if you think about it. So we're taking it down from 100,000 cells to 0 in 5 minutes. 10 to the 5 organisms, colony forming units. That is massive. A 5 log reduction is amazing in 5 minutes. So, UV light emission in any room, you know, the future of it could be quite astounding, because you could do the terminal clean of the room as the patient leaves the room, and then you could put your UV light in, operated for however many minutes are determined within your hospital, and you know that you're going to get a huge log reduction of organisms on the surfaces and in the air in that particular patient room. So quite dramatic. In real life situations, if we think about the shadowing problem, how do we get away from UV not working in a shadowed area? Are we going to have to open everything up? Are we going to have to turn things around? What's interesting about UVD robots are the fact that they can move. So they have the opportunity, and you can program the robot to move to near the area where the shadowing is occurring, and you still then have UV light actually being displayed in that area. And the tests that have been done in the laboratory, and certainly in our study, were done within a 1 metre proximity, and that's very important. A greater distance that the UV light has to travel, the less kill you get. So the study was actually created at Melbeck to actually determine how the robot may operate in a room. So we placed a robot in an empty facility. We placed 2 very large boards up in this facility, so it created shadows. We placed the stainless steel coupons with the organisms in the shadowed areas of this facility, and we allowed the UVD robot to move between the centre and where the shadowed areas were in 2 positions. So stainless steel discs, which we call coupons, were placed in these shadowed areas. We actually placed on the surface of these coupons, we placed a minimum of 10 to the 7 organisms. Now, when we talk about 10 to the 7, people can't visualise that. So it is 10 million cells are placed in 50 microlitre drop. We then allow them to dry on the surface for 30 minutes. We place them in the shadowed area and we then set up the experiments. And we decided to test some of the multi-drug resistant organisms that are very prevalent in hospitals today. So we looked at Clostridium difficile spores, we looked at CPE, carbapenemase resistant Enterobacteriaceae, and we chose a Klebsiella pneumoniae, which is known to be carbapenemase resistant. And we also used Acinetobacter baumannii, which again is an environmental organism causing lots of problems in hospitals. So we seeded the coupons with these organisms. We exposed them to UV light for a set amount of time, and we looked at 3 minutes, 5 minutes and 10 minutes, 15 minutes for spores only because spores are more difficult to kill. And we also had control coupons placed in the same positions. These control coupons were seeded at the same time. The control coupons were placed in a petri dish with wrapped up, triple wrapped with tin foil so the UV couldn't penetrate it. And the control coupons actually then were their own controls. We then took the coupons to the laboratory. We placed the coupons in 10 ml of diluent, vortex mixed them to knock any organisms off the coupons, and we serially diluted them so we can ascertain the viable count of the organisms. And that is the number of organisms that are still alive that are remaining on that disc. So bearing in mind we'd placed around about 10 to the 7, which is 10 million organisms on the disc when we started. So we had to do enough dilution so we could estimate the accurate numbers. We used UV indicators as well at the same time, and these UV indicators obviously change colour when they're exposed to certain levels of UV light. And you can see for the various organisms that have been tested before, MRSA requires 192 joules for a log 6 reduction, E. coli requires 180 joules for a log 6 reduction, and vegetative, not spores of C. difficile, requires 240 joules for a log 4 reduction. What the UV indicators demonstrated in the laboratory sessions that there was over 1,000 joules given to that area in any 1 minute. So we knew there was plenty of UV light coming from the robot, even in these shadowed areas that we'd set up. And they were, the UV light was killing or should kill the organisms. The study results were very exciting. Klebsiella pneumoniae, which is carbapenemase resistant. This showed a 6 log reduction of organism numbers in 3 minutes. Now a 6 log reduction, for many people who don't understand that means it's gone down from 1 million cells that were placed on the disc to no cells or 1 cell. So it's actually killed 1 million cells in 3 minutes. Acinetobacter baumannii, we saw a 7 log reduction in 3 minutes for this organism on the coupons. So that was a 6 log reduction in 3 minutes in both positions for the CPE, and a 7 log reduction in 3 minutes in both positions for the Acinetobacter baumannii. So what about the Clostridium difficile spores? Clostridium difficile spores are really well known for difficult to get rid of. We find them in Hoover bags, we find them in the environment in hospitals, and they can persist in dry environments for a long time. The coat of a spore is very, very difficult to penetrate. So we were expecting these to take longer to kill, However, what we saw was a 4 log reduction in 3 minutes and a 4.5 log reduction at 5 minutes in both positions. And this increased the longer we left it. But a 4 log reduction, that is taking it down from 10,000 spores down to no spores in 4 minutes. That's absolutely amazing results. So in conclusion, we were very impressed with the fact that we had a robot that could be programmed to move around the area to eliminate shadowing. The 2 positions that we placed the organisms in were in shadowed areas, but the robot was able to move around and be within 1 metre that was required to cause log reduction. Very impressive 4.5 log reduction in Clostridium difficile spores within 5 minutes. A 6 and a 7 log reduction in the 2 gram-negative organisms, CPE and Acinetobacter baumannii, within 3 minutes. So I certainly think without any hesitation, UV decontamination of the environment is something that we have to think of as a part of our end game and part of our infection control procedures going forward. Thank you very much. These particular bacteria were chosen for testing at Melbeck because they are problematic in the UK. The CPE is on the rise, Acinetobacter baumannii is on the rise, and C. difficile spores are very difficult to kill. Yeah, hospital-acquired infections are a real problem. If we've got people going in for cancer surgery or bone marrow transplants and they acquire an infection from the hospital environment, it's very, very difficult to treat with antibiotics. The worst case scenario is death. Therefore, it's essential that we keep the environment as clean as possible. We do terminal cleaning with disinfectants, but if you could then go in with a UVD robot and you know that you've cleaned the environment, you've caused a 6 to 7 log reduction in however many minutes you use the robot for, it means that you are decreasing the chances of environmental infection. We call these organisms superbugs. However, they're just like any other organism of the same group. They are resistant to certain antibiotics, and these antibiotics are the one that we've been using to get rid of them from the patient for many years. However, these antibiotics are now resistant, so we call in these organisms superbugs. However, they're no different to, say, methicillin-sensitive staph or normal E. coli in terms of their sensitivity to UV. So, you know, if you're trying to kill an MRSA, it should just be as easy as killing an ordinary methicillin-sensitive Staph aureus with UV. Certainly E. coli infections acquired from the environment. If you've got an E. coli sepsis, it's obviously not going to help the patient at all. But if you're trying to prevent the patient from acquiring an infection with E. coli, where perhaps it's residing in the environment, it might be residing in the wet environments, in bathrooms. If you can UV decontaminate a bathroom, you're going to reduce numbers of E. coli and you're going to reduce the risk of infection. Most UV devices are static, so you place them in an area, in a room, that will usually be within one metre of anywhere which could have contamination on the surface. However, you invariably get shadowing. You get shadowing of where perhaps a bed rail is, or a piece of equipment in the room. Behind that piece of equipment, you're going to get shadowing, so the UV isn't going to hit that area, so the bugs will persist. However, if you've got a robot that moves around the room, it can go to areas behind the obstacles and help, you know, make sure that the UV gets exposed to all areas and the shadowing is minimized.
Avantik